First thing is, well, do problems, practice, look at lots of problems. The more you look at, the better. Make sure you take care of your health. There's a temptation to be like, okay, I'm going to spend the next 30 hours and 40 minutes, give or take, just studying. No, give yourself a break. Get enough sleep tonight. Eat well tomorrow. Get out and do a walk at some point. You don't want to show up to the test and be mentally exhausted. This is not how you run a marathon. You don't show up at the start line tired. When you exit, it's okay to be tired. But when you start, you should be fresh and ready to go. The test itself, the problems are not technically demanding. So if you're like, ooh, they're going to give me like the craziest functions I've ever seen, you're going to walk out disappointed. But conceptually, we're going to test you. We're going to push you. Some people might be pushed a little bit out of their comfort zone. Probably most people will. I think there's one problem there. People are going to look at it and say, I don't think I've ever seen anything like that. But you know how to do it. The tools are there. And just relax. Pay attention. Don't just sort of do your first knee-jerk reaction. Think about what's being asked. And say, okay, I know what the question is asking of me, and I'm going to take my time and do that. Now, I asked at the last class, I said, look, if anybody has questions, email and we'll go over that. I got one email. So we're going to do that for the next 45 minutes. No. Well, probably about 10 minutes or so. So someone said, all right, I'm interested in the following. How do I handle really high order derivatives? Now, 2, that's easy. But what if I want to take, I don't know, say the 114th derivative of something? What do we do? So what's the answer? Well, the answer is you look for certain patterns. And the key to taking high order derivatives is, here's a few patterns you should recognize. First off, the derivative of, say, e to the kx is k e to the kx. That's not too surprising. That's the chain rule. So what happens is if I'm taking a derivative of, say, e to the kx, every time I take a derivative, I get hit with another factor of k. So you can imagine I take, let's say, n derivatives of that. Well, what will happen? Well, every time I took a derivative, I got a factor of k, so I'm going to end up with k times k times k, n times e to the kx. 1 for each derivative, so that's kn e to the kx. So that's an example when I talk about looking for a pattern. Now, if you want to look at, say, the derivative of, okay, let's do the nth derivative of x to the k. Now, there's a couple of cases. So I'm thinking of k here as a whole number. So sometimes you'll see the question, take the higher order derivative and you have x to a large power. Well, one thing that could happen is you're taking a really big derivative. So n could be bigger than k. And if that's the case, so think of it like I'm asking you for the 5th derivative of something that's an x squared. What's going to end up happening? It's going to be 0. Because what happens is every time you take a derivative, you knock the power down by 1. When you get down to power 0, that means you're constant, and one more and you're gone. Now, on the other hand, if n is smaller than that, here's what happens. Every time you take a derivative, the exponent comes down, and then it subtracts by 1. So what will happen is you're going to get k. You're going to get k minus 1. And then, I should have given myself more room. That's what's going to happen. Okay, you're going to get k minus 1, all the way up to k minus, then it'll be n minus 1, x to the power k minus n. So essentially, the important thing here is there are n terms. So really special case is if n equals k, then what you end up with is if n equals k, you get k factorial. Because when n equals k, you get x to 0, you'll get k factorial. And the other thing is, similar to e to the kx, if you look at derivatives of sines and cosines, and so the important thing about sines and cosines is to keep in mind that these tend to cycle. So this goes through a cycle of length 4. So what's the cycle? Well, the derivative of sine is cosine, derivative of cosine is negative sine, derivative of negative sine is negative cosine, and then you're back to where you started. And then for that, you just say, okay, how many times do I have to go through the cycle? So once you understand there are certain patterns you look for, and these are the ones we would expect you to know. Once you understand that, then you can do higher order derivatives pretty quickly. So you could say, well, suppose I give you a function, since it said 114. All right, suppose I say f of x, that's 3 e to the 2x plus 17 cosine of x plus x to the 114 minus 27 x to the 100 plus e cubed. Okay, what's the 114th derivative? Well, we go through it term by term. So f of 114x, from the first term, what will we end up with? Well, we're going to have a 3, and then we're going to get a bunch of 2's. How many? 114 of them. So 2 to the 114. You're probably thinking, well, what is 2 to the 114? And the answer is, it's 2 to the 114. You don't have a calculator. Don't try to figure it out. It's not worth it. Get the points. Get the points. Cosine of x. Well, cosine, you're part of the cycle. So if I start at cosine, now 114, what do you have to know? You have to think about what happens in terms of multiples of 4. So is 114 a multiple of 4? No, it's actually not. 112 is, because 112, that's 28 times 4. No, you don't need to know that, but okay. So 112, after 112, you'd be back to where you started, plus 2 more. So the 114th derivative of cosine would be negative sine. X to the 114, what's that going to be? Well, notice that the 114 matches with the 114. That's that special case of n equals k. That's 114 really excited. 114 factorial. All right. 27x to 100, what's going to happen there? Goes away. And e cubed, that really goes away. I didn't even make it to the first derivative. It's gone because it's a constant. And that's the answer. So if you want to talk about higher order derivatives, there's a few basic things to look for, but the real key thing is take a couple of derivatives and you're saying, oh, things are following a pattern. Use the pattern. The last thing we want you to do is do a lot of derivatives for 2 reasons. One, we don't want to actually check your work because we know it's wrong. But, from an ethical standpoint, we have to check it. And 2, it's going to take you way too much time. You want to use that time to get the points. Get all the points. Oh, there's a question. Yes?
So if you took 12 derivatives, and then that would get you back to the cosine. So if you do 2 more, would it be negative cosine?
So if you took 112 derivatives for cosine, it would get you back to cosine. So you can think of it as 114 derivatives, you can think of it as 112 derivatives, then 2 more derivatives. So I wrote sine? Oh my gosh. Well, okay, so I lost a point. Thank goodness there's a curve. Wait, maybe there's not. Who knows? Who knows? Okay, that was the problem I get to drop. I get to drop a problem. All right, good. Now, the other question that the person who sent an email asked is said, yeah, these limits in algebra and trig, they're shaking me. They're making me nervous. So let's mention a couple things. So for algebra, what do you need? Well, for algebra, I would say that basically you should look for 3 things. One, if you have square roots, you should say use a conjugate. So if you see a square root and you say, I need to get rid of that square root, conjugation, that should be your first reaction. And there you go. The other thing is if you have, say, fractions within fractions, get rid of them. And you're probably thinking, ooh, I like that style. I should do that. That should be every technique. So how do you get rid of fractions within fractions? Common denominator. So you get a common denominator, you add them together, and you can get it down to just a single fraction. So you should avoid fractions within fractions. And the last thing is, if you have polynomials, what should you be doing? You should be factoring them. Now you might say, will all polynomials factor? In the real world, no. On calculus exams, surprisingly often. And one of the things is, when you're dealing with limits, you oftentimes know ahead of time you have to factor, because if you get a 0, that means you know a root. And if you know a root, that means you automatically know a factor. So it makes it super easy. So when it comes to algebra and handling limits, those are the things that you have to remember to do. And if you can remember those, any algebra you can handle. Now, what about trig? Well, for trig, I would say there's two things to remember when it comes to trig. First off, we're not going to test you on obscure identities. So don't go home and be like, I'm going to pull out my list of 101 obscure identities from trigonometry. Now, you might say, well, what's not obscure? You should know some basics. I would say the following is fair game for right now. Sine squared plus cosine squared. I'll test you. What does that equal? Okay, good. Got that one right. Tangent squared plus 1. What does that equal? Secant squared. Ah, good. 2 for 2. If I see sine of 2x, what can I replace it with? 2 sine x cosine x. A little bit more hesitation on that one. Cosine 2x. Cosine, not a lot of hesitation. Cosine squared minus sine squared. I would say these right now are fair game. So I can, if I put anything on there that requires one of those 4 identities, I don't need to give you that identity. Any other thing I put on there right now, I would expect to give you an identity. So you don't need to know lots of trig identities. So what do you need to know? There's 2 things you have to remember when it comes to taking limits with trig. And here are the 2 things you have to remember. First off, step 1, write everything in terms of sine and cosine. That's it. You don't want tangents, you don't want secants, you don't want cotangents. Everything becomes sines and cosines. And that's what you're going to do. And the second step is remember the limit as blah goes to 0, sine of blah over blah is equal to, do you remember? 1. That's it. If you remember those 2 facts, that's all you need to handle anything that's trigonometry. Now, you might say, is that really all I need? Yes. Really? Okay. Look. Here's an example of something that you might object to and say, I'm not sure if that works. Let me pull up a problem from last year. Because you might remember, well, I don't know if you've looked yet. Here's an exam from last year. As a reminder, we have adjusted the difficulty level because there's more problems and less time. So we're like, okay, so the difficulty level is probably a little bit turned down from here. But now that we look at it, we're probably like, yeah, let's look at this one. So I want to understand what's happening at 0. So limit x goes to 0, 1 minus cosine of 3x over x tangent of 2x. Now, going back to our philosophy, what's something we should do here? We don't want tangent because that's not sines and cosines. What do we do with that? Yeah, it's sine of 2x over cosine 2x. So we say, hey, problem solved. So I'm going to replace this by x sine of 2x over cosine of 2x. Now, I don't like fractions within fractions, so I can move the cosine 2x upstairs. So that becomes the limit as x goes to 0 of 1 minus cosine of 3x times cosine of 2x over x sine of 2x. Now the problem is we're going to be going, whoops, sorry, I'm off the screen. We're going to be going to 0 over 0 here, and you're probably saying, Steve, I don't know how to handle that 1 minus cosine. But remember, there were some things that we can do. So, how do we solve 1 minus cosine using the ideas here? The answer is we combine a couple of ideas. We use the fact that sine squared plus cosine squared equals 1, which lets us say if I have a cosine squared, I can replace it with a sine squared. We say, great, but how do you make a cosine into a cosine squared? The answer is, think of it as conjugation. Because what conjugation is really doing is it's squaring stuff. So, we're going to multiply by the conjugate. So 1 minus cosine 3x, what's the conjugate? 1 plus. So you get 1 minus cosine of 3x. You're going to get a 1 plus cosine of 3x. You get a cosine 2x, that's still there. Then downstairs you get a 1 plus cosine of 3x. Then you still have that x sine of 2x. Now, the 1 minus cosine squared of 3x becomes what? 1 minus cosine squared, which becomes sine squared, using our identity. So limit as x goes to 0. And I'm going to write sine squared in a very fancy way, namely as sine of 3x times sine of 3x. And now that's that part. And cosine 2x, I'll write that as cosine of 2x. Over, downstairs, I'm going to have the 1 plus cosine of 3x, the x, and then I'm going to have a sine of 2x. Now, what happens next? Well, now we pull out the blah. We say, hey, if I can make it look like sine of the inside matches what's underneath, that goes to 1. So everything that's a sine, because the signs are causing the zeros, we're going to go through and update them. So here we go. Let's update. Sine of 2x, I want what's underneath the sine of 2x? I want 2x. Now I can't just put 2x there, but I can put a 2x if I put a 2x as there as well. Sine of 3x, what do I want underneath there? 3x. So I'm going to put a 3x here as well. Sine of 3x, I'll put over 3x. I'm going to put a 3x as well. So I've basically done a lot of 1s. Now, stare at this for a second, but not too long. We don't want to lose our sight if we stare into the sun. See, we have an x here and an x here. That's an x squared. You have an x here and an x here. That's another x squared. Those all cancel. Now let's talk about the pieces. What does sine 3x over 3x go to? 1. This sine of 3x over 3x? 1. This cosine 2x? That's a 2x. It looks like a 2y because of my bad handwriting. Goes to cosine of 0, which is 1. Sine 2x over 2x goes to 1. 1 plus cosine 3x goes to 2. So what's left? 3 times 1 times 3 times 1 times 1 is 9. 2 times 1 times 2, 2 times 2 times 1 is 4. 9/4. That is more complicated than anything that we'd ask tomorrow. But if you think about the actual principles, there's just a couple of them. Put everything in terms of sines and cosines. If you see a 1 minus cosine, conjugate it to make it a sine. When you get down to that part, make sure you get sine of something over something. Make things match, and then you're home free. Life is good. Life is good. All right, well, that was an example with trig. Do you need to see something with algebra, or are you convinced? You want to see stuff with algebra? All right, well, we need more convincing. There was a question that was also asked. This was a moderately long email saying, would we have to use the definition of the derivative? They didn't phrase it this way. The definition of the derivative with a trig function. And the answer is, that's tough. The reason it's tough is to do the definition of like sine, or with cosine, you need a trig identity. Unfortunately, you don't need these trig identities. You need more obscurish trig identities. I don't want to say too obscure. They're not super obscure. You can do a few things. So here's something you can do. And then I'll do an algebra one. So given that we know that the limit as h goes to 0 of sine of x plus h minus sine of x all over h is cosine of x, which is just a fancy way of saying, if you look at this expression and you just happen to walk down the street and say, hey, sine of limit as h goes to 0 of sine of x plus h minus sine of x over h, would you recognize what that is? It's a derivative. It's the function x plus h minus the function at x over h. And what's the function? It's the sine function. And the derivative of the sine function is cosine. So given that you know that, use the limit definition to find the derivative of sine squared of x. Okay. So now we're not going to use anything other than the limit definition and the fact we already know. So how can we do that? Well, we start by the limit definition. So make sure you know your limit definition. H goes to 0. Then what you do is you take whatever you're taking the derivative of, and everywhere you see an x, you put an x plus h. Subtract. Everywhere where you see you just put it in the function. Subtract sine squared of x all over h. Okay, so a first step, whenever you're asked to use the limit definition, is apply the limit definition, just literally what it says. Now, what can we do? Well, we don't need to conjugate here because things are already square. Somehow we want to, unsquare. Take a minute to factor what should be the right step into this problem. What should we do? Oh, we should factor. See, because really it's something squared minus something squared. Difference of squares, that's one of the bread and butter things that we do over and over again. So that's the limit as h goes to 0. So it's sort of say, a minus b times a plus b. So that's what we can do with the top. And then we say we have the bottom. Well, notice sine of x plus h minus sine of x, that matches with what we know. So let's put the h underneath. Now we have two things. What does the first one go to? Cosine x, because that's what we know. We can use what we know. Cosine x. What does the second part go to? Well, to figure it out, plug in h equals 0. And here, we don't have anything in the denominator, so there's not going to be some crazy 0 over 0 issue. It's going to be sine of x plus sine of x, also known as 2 sine x. So we end up with 2 sine x cosine x. And so there's the derivative of sine squared. So once you have the limit definition for the derivative of sine, you can use the limit definition to get the derivative of sine squared. All right, so people want to see limits. Okay. Should we do a limit definition of a derivative involving something algebra-like? Yeah. Okay. Suppose f of x is 1 over x plus 3 square root of x. I'm going to already regret this now that I've written it down. Let's do the limit definition. So do the limit definition to find, if I can spell, f prime of x. So the first step is you say f prime of x is the limit as h goes to 0, f of x plus h minus f of x over h. You put this down, you get your 2 points, and you're like, okay, good, I'm not getting 0. I'm not going to be that one person on the exam who didn't even bother to study the limit definition. I'm getting those 2 points. I'm going to get it. Okay. All right. Well, 2 points is 2 points. Yeah, we want them. That's like better than 1 point. You know, that's good math. Okay, now comes the hardest part. And I don't remember exactly how we break points down for these types of problems. But usually it's like 2 points is the definition of the derivative. And then like 2 points for the next step. And the next step, you're like, what's the next step? Must be a really cool step. It's plugging in x plus h. And you're like, what? Is that hard? The answer is no. But people messed it up. So we have to put points on it. So how do you plug in x plus h? You literally go into your function. Everywhere you see an x, you put an x plus h. And that's it. That's it. It's like, we've already got almost like 3 or 4 points. And it feels like we've just started. Because, yeah, a good start is worth something. Now comes the algebra. So, what do we start doing? We've got fractions here. What do we want to do? Get a common denominator. So here, the common denominator would be the product of these two. So what you'd end up doing here, you get a limit as h goes to 0. You're going to have x plus 3 root x in the first term. That's where you multiply x plus 3 root of x over x plus 3 root of x. In the second term, you'd have x plus h plus 3 square root of x plus h. And then, again, that's because you multiply top and bottom by that, all over x plus h plus 3 square root of x plus h times x plus 3 square root of x. Notice, it's not to your advantage to expand. Don't expand unless you think it's to your advantage. And finally, this 1 over h downstairs becomes just an h downstairs here. Now, as you come into this type of problem, when you see something that's algebraic, and like I'm taking a limit definition of algebraic, we have a goal. Our goal is to cancel some h's. That's our goal. Because the h is what's going to be causing our zeros downstairs. So we're going to want to make the numerator look like an h attached to stuff. So we want to get to h over h. And if we live a good, healthy, clean life, it's going to happen. And if we don't, we're going to be sad. And I can already tell I'm regretting my decision. But that's okay. What happens next? We can cancel off some x's upstairs because you have an x and a minus x. And now, this might be a 2-pager. Limit as h goes to 0. And you're probably thinking, how does he know that? Well, I chose poorly. No. 3 square root of x minus h minus 3 square root x plus h. So remember that the minus sign, this is a place where a lot of people lose points. That they forget minuses distribute. So make sure if you have a minus, it distributes. Actually, we're okay. We're back on track. Life is good. Life is good. Downstairs we have h times x plus h plus 3 square root of x plus h. And another place that people make mistakes is copying. It's been so fascinating to watch. Like, sometimes you'll see if someone says it's a 4, and you're like, clearly that's a 4. And then on the next line, 4. And then on the next line, 4. And then all of a sudden, it's a definite 9. And you're like, what? And you're like, well, it's a 9 at the answer. I'm sorry. I'm going to have to minus 1. But, pay attention. Copy well. There's no points for finishing fast. There's points for finishing correctly. Okay. All right. Now, we're in our conjugation mindset. We want to multiply by the conjugate. However, there's a challenge here. What's the conjugate? Because conjugate means you have like a minus b multiplied by a plus b, which means there's 2 things. But notice, these are 3 things upstairs. So we have to group. Now, what's the logical grouping? Now you might say, there isn't a logical grouping, because no matter what, you're going to have a square root at the end. But let's think about what we want to achieve with our conjugation. Our goal for conjugation is to get rid of square roots, but really what we're trying to do is manipulate the h's. This h is our bad h, because it's inside that square root. So we want to really get that h out of the square root. This square root doesn't have an h, so we're like, I'll live with it. Which means when it comes to conjugation, that's our choice. We're going to group those first two terms together and then our last two terms together. So multiplying, we get 3 squared root of x minus h plus 3 squared root of x plus h. Then we have downstairs 3 squared root of x minus h plus 3 squared root of x plus h. All right, let's just cross that off. People are going to try to figure out, what does that mean? What does that mean? What's that blue line there? All right. Now, we're making progress. We're getting close. We're getting close. Limit as h goes to 0. And, okay, multiplying this out, we'd have 3 squared root of x minus h times 3 squared root of x minus h, which is 9x, because I'm basically squaring this. So a squared minus, and then cross multiply, you'd have 2 times 3 root x times h plus h squared. Then you're going to have minus this term squared, 9 times x plus h. All divided by a lot of stuff. All right, how you doing? Hanging in there? Yeah, okay, all right. Do you think we're close, or do you think we're not going to make it? We're going to make it. We're going to make it. I can feel it. We're so close. Now, have we lived a good life? Well, you know you've lived a good life if cancellation happens, which is a good cancellation. So, does good cancellation happen for us? We have this 9x here. That doesn't have an h. And remember, our goal is to cancel h's. So we don't want anything left that doesn't have an h. Does that cancel? Yeah. See, there's a minus 9x over here. We've lived a good life. Good for us. How about what's left? Everything that's left has an h, which means I can pull an h out and cancel. So, if you pull an h out and cancel, then on the next line, you'd have the limit as h goes to 0 of, let's see, minus 2 root 3x, that h cancels, plus h minus 9. All that divided by h times x plus 3 root x plus h times x plus 3 root x times 3 root x minus h plus 3 root x plus h. Okay? Oh, and I canceled the h's, so that h is gone too, sorry. I pulled an h out and I canceled. What's left to do?
It's 2 times 3, not 3 root.
Oh, you're right. It's 2. Well, what you didn't notice is this is really that the square root extended, and there was a very hard to read root 3 there. But you know, I should have made it more clear when I wrote it down. Okay, fine. Now I have to drop 2 problems. Wait, I only get to drop 1. Darn it. Okay. All right. Well, thank goodness for the curve, if there is one. All right. What happens now? We're ready to finish it up? What's the last thing? Because we haven't finished yet. You're not done until you've evaluated h equals 0. So you put in h equals 0, and the nice thing is, upstairs we get minus 2 times 3. I guess I should have written that as 6. Minus 6 root x minus 9. Divide that by x plus 3 root x times x plus 3 root x. So that's x plus 3 root x squared. Then here I'd have 3 square root of x minus h plus 3 square root of x. So that would be 6 square root of x. And that's the answer. Now, we're paranoid. We're like, I'm not sure. I'm not sure. He messed up a lot on this problem. I'm not convinced he did it right. How can we check? Yeah, look, even though it says use the limit definition, we're allowed to check by using another method. We won't get any credit for checking, but at least we'll be more satisfied. So let's just check to see if we did this right. To be honest with you, I'm not even sure myself. So this will be exciting for me, you know. Let's find out. So the derivative, when I see something like 1 over x plus 3 root x, I often find it easier to think of this as x plus 3 root x to the negative 1. So that's minus x plus 3 root x to the negative 2 times the derivative of the inside. What would that be? Well, that would be 1 plus 3 times a half times x to the minus a half. Now, we can do a couple of things. Let's multiply top and bottom by something. Well, let's okay, so minus 1 over x plus 3 root x squared. And then here, what would I do here? Let's put a, 1 plus 3 over 2 square root of x. That's what it is, I mean, if you write it out. Now, looking at this, you might think, I don't think you did that right, Steve. But notice what we can do. Common denominator, right? So this thing we can write as 2 root x plus 3 over 2 root x. And then what can you do? Well, let's multiply it by 3. 6 root x plus 9 over 6 root x. And the minus, because you see the minuses here? The 6 root x plus 9, 6 root x and 9. The 6 root x downstairs. And the x plus 3 root x squared. So that was correct. It worked out. It's all there. Now you're not even sure if I did that part right. Now you're really suspicious. It's there. It's there. Okay, again, that one would be harder than a problem we'd ask. Okay, so we still have, 12, 15 minutes, give or take. I did print out all the old exam prompts so we can just fly through them and say, do this, do that. Or we can finish early, or I can take questions. What would you like?
We have a problem.
Oh, there's a problem here. Really? Again? Yeah. You guys really like the... there's not going to be like 5 of those. But okay, all right. Limit definition.
The square root of x squared plus 4.
Isn't it like a quiz problem?
I found it on the one of the old exams.
It's a lot like a quiz problem. So, I mean, what would you do? You do the limit definition, square root x plus h squared plus 4 minus square root of x squared plus 4. What happens here? Conjugation. Yep. And that's a plus. And from here, it's not so hard to see what happens. What will happen? Well, upstairs, you're going to get the x plus h squared. That's x squared plus 2x h plus h squared plus 4. Subtract x squared plus 4. And, of course, we want full points. I will say, we take off points for bad notation. So don't have bad notation. Have good notation. And we want to get all the points. So we've lived a good life. The x squareds cancel. The 4's cancel. Everything else has an h in it. Those cancel. And now we're saying, aha, plug in h equals 0. We get 2x upstairs. Downstairs, square root of x squared plus 4. Another square root of x squared plus 4. Leaving us with the final answer. There's an add sign there of x over square root of x squared plus 4. So, all right. I'm sorry, I have bad hearing. How much do the something something count?
Unit circle, how much do we need to know the unit circle?
How much do you need to know the unit circle? I would say you should know 0, pi halves, pi, 2 pi, spoiler alert, equals 0. And for good measure, throw in pi fourths. And that's it. That's what we expect you to know by heart. I hear the people like, oh, my trig teacher lied to me. They said that in college they'd have to know all of the circle. Man, I'm just starting to suspect these high school teachers, they just don't have your interest at heart. There's another question. Spring of 19, what does the question ask? Okay, so we need to, is it this one?
Yes.
Okay. So particles position in meters at time t in seconds is given by the following function. So you have this function, a and b are constants, and you have a problem that says find an a and b. We like these kinds of problems where it say, hey, find a and b which satisfy certain things. So when you see problems like this, the key is to realize, okay, so you have position, and then you say, okay, velocity. What's the relationship between position and velocity? Derivative. So really, velocity is 0, means s prime t equals 0. Acceleration, what is that? Second derivative, s double prime. And is, unfortunately, bad spacing, equals 0. So this problem says, hey, if you take two derivatives, either the first derivative and the second derivative, you're both going to get 0 at time 0. Lots of zeros. So we just need to take a bunch of derivatives and evaluate them at 0. Now, how do you take the derivatives? I would recommend, because this has the form of a number over a function, I like to write this as 4 times t minus 2 to the negative 1. A sine t, 1/3 b, e to the 3t. So s prime, well, the negative comes down, so it's negative 4. T minus 2 to the negative 2, the derivative of the inside is 1, so that's good. Then plus, derivative of sine is cosine. And then 1/3 b, derivative of e to the 3t, the 3 comes down. So 1/3 times 3 becomes b. We're going to need the second derivative, so we might as well take that while we're thinking derivatives. Here, negative 2 comes down, so we're going to get plus 8. T minus 2 to the negative 3. Derivative of the inside is 1. Derivative of cosine, negative sine. And here, the 3 comes down again, so we get 3b e to the 3t. All right, so those are our derivatives. Now we say s prime of t. Well, s prime is 0. Plug it in. We get negative 4 over negative 2 squared plus a times cosine of 0 plus b times e to the 0. Well, negative 2 squared is 4, so that becomes negative 1. Cosine of 0 is 1, so that's a. And b, e to the 0 is 1. So we get negative 1 plus a plus b equals 0, because s prime is 0 is 0. Whoops. S prime is 0 equals 0. S double prime 0 equals 0. All right, so we now have one equation. So whenever you're solving for a and b, you should expect two equations. That's our rule of thumb. Second equation. S double prime is 0. Well, we get 8. Divide that by negative 2 cubed minus a times sine of 0, and then plus 3b e to the 0. Well, e to the 0 is 1. So negative 2 cubed is negative 8. 8 over negative 8 makes negative 1. Sine of 0, 0, so that's gone. And negative 1 plus 3b, and that equals 0. So we have a second equation that says 3b has to equal 1. Well, it turns out these are the kind of equations we like, because we can solve pretty quickly. From the second equation, you solve for b equals 1/3. Then you say, well, something plus 1/3 has to give us 1, so the something better be the 2/3. And there's our a and b. Now here, it was kind of easy because they said, oh, find a and b. Sometimes they'll be like, look, we'll give you the function, but then you have to find the velocity. And if you do, make sure you pay attention, because if a problem says include units, what should you do? You should include units, yeah. It's secret code for like, do what the problem says. It's amazing. It's amazing. So, I think most of these are, hopefully you've seen enough, and it looks like you're packing up, so I guess we'll call that a day.